we are going to take up the question of finding area between the graph of this function, which is shown here between 0 and 1, and the x-axis. So we mean that we would like to compute this area, and we are going to employ the upper Riemann sums, or the upper rectangles, or the rectangles that we form by using the right end point of a partition, okay, and adding them up to approximate this area. So let's start with, say, 5 different rectangles, and we shall take the altitude of those rectangles according to the functional values determined by 0.2, 0.4, 0.6, 0.8, and 1. Okay, so I'm just going to use this package to show you how do we get an how do we get a picture. So here it plotted an approximate integral, but it's giving us a lot more than we are concerned with at this moment. Okay, so let me ask it to be confined to the region of our interest, and we want the upper boxes here, and I'm going to take 5 of them. And I'm not teaching you the software, even though I love this software, but yeah, just for the sake of convenience, I'm just using it here. Okay, so what we will do is that this area that we wanted to compute here, we will approximate it by the sum of these 5 rectangles. So let's look at these 5 rectangles. Each of them is 0.2 units wide, right? So the first rectangle has a base of 0.2 units. And how much is the altitude? The altitude is determined by the value of this function at 0.2, which means that I just take the function at 0.2, okay, and here we go. So that's our first rectangle, right? How do we get the second rectangle? It's again the same width here, or the same base, and instead of taking the altitude according to 0.2, now we are taking what? 0.4. okay, so now we are going to go to this point. So yes, let's go there. Okay, so here we go to 0.6 to the power 4, okay, and going so on and so forth. We have 0.8 to the power 4, and at the end we have what? We simply have 1. All right, so we have this is the first rectangle, the altitude determined by this. The second one, the altitude is determined by this. This is the third one, this is the fourth one, and this is the fifth one. Okay, and if we compute the area, it says equal to a certain degree. It's approximately how much? What is shown here. Okay, now what we are going to do is that we are going to increase the number of rectangles, or in other words, we will make these the length of the bases narrower. Okay, now we do not want to write this big expansion every time we work on it. So notice this, we can have a short form in the summation notation for this whole thing in the following manner. That is, notice each one of them is 0.2 units wide. So that part is easy. So what I'm going to do is this. Let me take this summation. Okay, so each one of them is 0.2 units wide, right? Now comes the question of the altitude. Okay, so for the altitude, what I got this, that they are square root of 1 plus, oh, I'm sorry, no, I should not be sorry. I think I'm doing all right. Yes, it's 1 plus x to the 4. I'm sorry. That's okay. All right. So here we got 1 plus, then the value of this variable, okay, which is determined according to what? We have 5 rectangles, so I'm taking 1 over 5, okay. And then what happens? I have 5 such rectangles. So this one is 0.2, then this is 2 times 0.2, that is 2 over 5, and this is 3 times 0.2, that is 3 over 5. This is 4 times 0.2, and this is 5 times 0.2. So we are using this summation notation. So what we are going to do is that we will use this variable I for this whole thing, and we are going to designate that our I varies from where to where. I is the variable. I could have taken X, but I is more typical as you might have seen. And if I did that, then notice this, I should still get the same answer. No, I did not. Okay, I see what I did. I forgot my power 4 here. Okay, all right. So first of all, let me apologize for making this mistake. Okay, so here you go. So we have, what we got here is, we got to the power 4, and there we go. We have the same thing. So it was a good thing that we checked it by expansion, so that otherwise, if I had carried this mistake along, then, you know, we would have realized it after like longer than we wanted to. So anyways, now what I'm going to do is, since I'm going to increase the number of rectangles, and this width here, it depends upon the number of rectangles, right? Here I have 5, and the whole interval is 1 unit wide, so I got this as 1 over 5, okay? So it may not be a bad idea to write 1 over 5 instead of 0.2, okay? And let's see how this helps us in further refining our values, okay? So here we go. So we got the picture again. Now we are going to do this. Yeah, let's try putting, say, 10 rectangles in there so that we have a better approximation. And we of course do have a better approximation because we have, you know, much less extra area coming in here in our computation as compared to this portion here. Okay, so what goes on here now is that now each rectangle is 1/10 unit wide, right? And we are going in the, you know, in the increments of 1/10 here. And how many rectangles I got? I got 10 of them. So this is an upper Riemann sum for again computation of this area. And if I compute, of course, I'm going to get a lesser value now. Okay, so it's 1.11, etc., etc. And we can go on refining it, like, see, we have this here. And then again, let's choose how many rectangles should we choose this time. Let's try 50. Okay, so yeah, we are doing much better. Okay, so here we go. All right, now I change this to 50, change this to 50. We don't have to forget to change this to 50. Okay, all right, so this is like we are getting closer. And let me just try one more. Okay, and I am doing it in a kind of in a live way, even though I'm not doing it right in front of a class, but I don't have time to repeat the whole thing, so I hope I get everything right. Okay, so here we go. Okay, so what happens is that we get 100, we have a 100. All right, we have a 100 here again. Let me check again here, right? Okay, good. All right, so here we go. Okay, and so you saw this in the definition, that when we keep on increasing the number of rectangles, or we keep on reducing the width of the partition, okay, or in the ideal case, when we put a limit on the, or when we want the width of the largest subinterval to be as small as we please, then all these sums, they approximate the area that we desire. And here, it looks pretty close. We know that there is something, extra in here. So let's go ahead and go to the definition. That is, this by definition should be what? Approximately 0 to 1. Definite integral of who? 1 plus x to the power 4 dx. And let's see how good an approximation have we gotten by taking 100 rectangles. Well, that's not too bad. Okay, if we had taken more, okay, then it would have been better. Okay, so let me see if I'm saving it, because if I challenge it too much, then sometimes it freezes. Okay, let's see. What I have is, well, yeah, that's not too bad. Yeah, we are getting closer and closer. Okay, so this is an idea of the upper Riemann sum. Okay, and if we wanted, we could compute the lower Riemann sum in the following sense. That yeah, let's just go ahead and get our earlier rectangle back. Okay, so in this case, say we did this, we wanted the lower sum. Okay, so what we are going to do is we'll say and lower boxes. So now we are going to underestimate the area. So in this case, what will happen? We will the altitude of each rectangle will be determined by the lower end point. Okay, so if I am adding the areas of these 5 rectangles, what shall I have? I'll have this. I'm sorry. Let's go to this. Okay, I can still have I from 1 to 5, and each rectangle is still 1/5 unit wide. All right, and then when we compute the altitude, what happens this time? Instead of starting at point 2, which is 1 times 1/5, we are starting where? At 0. So we just have to put a slight modification here, that we can say, well, this is I minus 1 over 5. So that way, when I is 1, this is 0. When I is 5, okay, then this is 4 over 5. That is 0.8, the area of this rightmost rectangle. Okay, and let's put power 4 here. Okay, so, well, of course, this is going to underestimate. But again, let's see, we did this with 1,000 rectangles. Okay, all right, so here we go, 2, 3, 1,000, 1,000, and 1,000 again. Okay, so there we are. Okay, and what was the upper sum? We just had the upper sum. Where did the upper sum go? Right here. Okay, that we had computed. And well, in this particular case, we can conveniently find it in between those two. This is slightly more and this is slightly less than what? The area, which is the definite integral from 0 to 1, square root of 1 plus x is not x square, x to the 4th dx. Okay, and there we go. So this value is in between these two. Okay, so yeah, I'll post another example very soon, and I'm going to post a script of this in our web page. Okay, all right, so let me know if you have any questions. Now, I computed these sums using that software called Scientific Notebook. Now let's try using our calculator, that is TI-84, to get the sum of these terms. So see, what we are doing here is that we got this sum, which we abbreviated as this here using the summation notation. And here I just did this, changed I to x, okay, just because the calculator will take x more conveniently. Okay, so what we are doing here is this, that notice we are obtaining the sum of what? 5 terms here. Okay, so we are obtaining sum of a sequence, all right, that is defined in terms of x, that put, okay, so sequence as a, let's say sequence is a function of x, all right, and of course we are going to go for only a finite values of x. Okay, so in this case we are going from 1 to what? 5. All right, so let's pull up the calculator. It's right here. Okay, now, and we want to compute what? Sum of this sequence given by this. Now we can look for these terminologies from the catalog, but in this case if you just went to this list option, okay, go to math, this sum is right here. Okay, then go to list again, go to options, the sequence is right here. Okay, and then my sequence is defined by, okay, here we go, it's square root of 1 plus, and then what? X over 5, okay, to the power 4. All right, and then we have x here, and then we are going from where to where? 1 to 5, and let's see what we get. Okay, we did pretty good. We approximately got the same value, and of course the scientific notebook took us much farther. Okay, now so this was the way we entered it. Now let's say we have to obtain, or we want to obtain this value here. Okay, that is for a Riemann sum of 100 rectangles. Okay, so let's pull up the calculator again. Now what I did here is this, just to avoid any syntax error for convenience, I went ahead and entered the function already. Okay, so because in this case, instead of writing the entire expression the way we did before, I can just pull this y1 up the way we worked on Newton's method. Okay, so first let's quit out of here, otherwise it'll overwrite things for us. Okay, so here we go to list. All right, math, then we are going to go to sum. Okay, I could have gotten through second enter. Let me not just say too much here. Okay, so there we go. All right, sequence. Okay, now what do we need? We need a y variable, right? So, and that we entered as y1. You could have entered it directly, but there'll be too much entering here if you did that. Okay, so we have x, then we got to 1, and how far are we going? We are going through 100. Okay, let's see what we're going to get. Okay, all right, yes, and then it stopped right here, right? Okay, good. So that's how you can use the calculator to obtain these values. Okay.